In this video, I'd like to show you how to do problem number 22. Now, in this problem, it refers to a glass bead that has been charged to 6 nanocoulombs sitting in the center of some spatial region here. So by whatever means this bead has acquired enough positive charge to go up to about 6 nanocoulombs in its total Q. And I want you to find the electric field 2 centimeters from the charge. So I'll just select some point here which looks like about 2 centimeters from the charge right here, and I'll draw a connecting line. And there's my point right there, 2 centimeters. Now, of course, there's a lot of points on this piece of paper that are 2 centimeters from the point charge, or excuse me, from the glass bead. There's one here, and one here, one up here, one up here, one up here. All of these points are 2 centimeters from the charge. That's the nature of the calculation about this electric field. So there's a whole bunch of points that are 2 centimeters from the charge here. In fact, any point on a circle of radius 2 centimeters is a valid point that's 2 centimeters from the charge. I'll continue to use this one right here because that's the one I sort of started with originally right there. So there's where I'll find my electric field. The electric field equation is a pretty straightforward application of it in this problem here. It's k times q over r squared. It is a vector equation, so we'll put all the r hat and the vector sign over the e in there. There's the equation we're using. To start the problem, we'll just find the magnitude of the electric field. So the magnitude of the electric field at 2 centimeters from the point charge is going to be 9 times 10 to the 9th. That's my value for k. The q here is a 6 times 10 to the minus 9th coulombs. And the whole thing is 2 centimeters from the charge, which is going to be 2 times 10 to the minus 2 meters squared away from the charge. So just a couple of cautionary points when you plug in these numbers here. Remember to always use coulombs, so I didn't put in 6 nanocoulombs. I put in 6 times 10 to the minus 9. And also I was careful to convert my distance into meters here because it calls for meters. Owing to the fact that we're using 9 times 10 to the 9th, we have to use meters in that case there. So if I plug all these numbers in here, the magnitude of the electric field I'll get 2 centimeters from this glass bead here is something like 135,000. And the units can either be volts per meter or newtons per coulomb, either one of those. Okay. What about the direction, though? Because it is a vector quantity. What are you going to put for the direction? Well, if you go back to the figure here, the direction of the electric field at this point here is sort of up and to the right. That would be the answer here. But if you chose this point, it would be down and to the right. This point would be down and to the left. This point would be up and to the left. So which one do you choose? Well, they're all correct because any one of these points would have been a valid point 2 centimeters from the charge. So the point that I'll put in here is something like outwards. You'd have to agree that the electric field at all of these points, no matter which one I chose, is definitely pointing outwards. And I can qualify that a bit more by putting radially. The electric field is definitely radially outwards. And I get the word radially because, of course, all of these field points are on a radius of this observation circle here, so I'm radially outwards. That would be the answer then. 135,000 volts per meter radially outwards would be the complete answer. I mean, just keep in mind if it was a negative charge, minus 6 nanocoulombs, for instance, here, the field value would be the same, but the direction would be radially inwards.